That's how we concluded our previous lesson introducing the physics of beat frequency with a pair of audio tone generators. That's a sound quite familiar to ham radio operators who tune their receivers across the shortwave radio band with the receiver's BFO, the beat frequency oscillator, turned on. A beat frequency oscillator is essential in a shortwave radio receiver for detecting Morse code transmissions and for deciphering single sideband voice transmissions. And this brings us to the first stage of actually building a metal detector and understanding how it works. Text sites which demonstrate how to build an authentic metal detector provide schematics for complex circuits that are a bit daunting for middle school students to assemble during a science lesson. And as every electronics hobbyist knows from experience, the more complex a circuit is, the greater is the probability for something to go wrong. The reason for this complexity is that the heart of a metal detector consists of a pair of radio frequency oscillators. Fortunately, there's an easy workaround for this complexity, so we can create a working tunable radio oscillator that we can construct on our snap circuits board with very few components, which we can use in our metal detector. But first we need to understand what an oscillator is and how it works. We've all had the experience of sitting in an audience where a microphone is being used, and either the volume of the amplifier is turned up too high, or the microphone comes too close to the loudspeaker, so that we hear a loud, deafening tone. What causes that tone? It's called feedback. The microphone picks up sound coming out of the loudspeakers and sends that sound back into the amplifier, creating a self-feeding loop. In the world of electronics, that's exactly how an oscillator works, through a controlled feedback loop. A very simple radio frequency oscillator that is easy to build is this one. The heart of the circuit is a common integrated circuit, a chip, that we refer to as an operational amplifier, or op-amp for short. This is a useful device for a ton of applications. It consists of two inputs. When a signal is fed into the port marked positive, that signal is amplified and comes out the other end in the same phase as it went in. In other words, when the input voltage rises, the output voltage also rises, even to a greater extent. And when the input voltage decreases, the output voltage also decreases. This is really important because we need an amplified feedback loop that will make the circuit oscillate and generate the tone that we want. When a signal is fed into the port that is marked negative, that signal is amplified and emerges with the phase inverted. In other words, when the input voltage rises, the output voltage decreases. And when the input voltage decreases, the output voltage rises. And this is helpful because we can use the negative feedback loop to precisely control the frequency of oscillation that we want. In the case of a radio frequency oscillator, that control is handled by a combination of a coil and capacitor. In other science lessons, we have already learned that a coil of wire has some interesting and useful electromagnetic properties. And we learned that a capacitor, which is simply two sets of metal plates in close proximity to each other, has interesting and useful electrostatic properties. And when we combine a coil and capacitor together, radio magic happens. They form a tuned circuit that resonates at a very specific frequency. Much like a guitar string, when strummed, vibrates at a specific frequency determined by the length and thickness and tension of the string. Or an organ pipe resonates at a frequency determined by its length and diameter. In a similar way, the frequency of alternating current at which this circuit resonates is determined by the combined electrical values of both the coil and capacitor. When either of those values increase, the resonant frequency decreases. Much the same way when a trombonist wants to produce a low note, he lengthens the slide on his instrument. and when he wants to produce a higher note, he shortens the slide. Decreasing the value of either the coil or capacitor raises their resonant frequency. One easy way to make small adjustments in the resonant frequency in a radio circuit is with this device, a variable capacitor. The variable capacitor that comes with the snap circuit kit looks like this. In our oscillator circuit, the operational amplifier wants to oscillate at any frequency that it can through the positive feedback loop. But the negative feedback loop prevents that oscillation from actually locking in at all frequencies except one, the resonant frequency to which the coil and capacitor are tuned. At that frequency, the combined coil and capacitor act like a resistor, preventing the amplifier's output signal from feeding back into the negative input terminal. So at that frequency, and only at that frequency, the positive feedback loop is free to kick the operational amplifier into oscillation and generate a radio signal at that frequency. However, if we change the properties of either the coil or the capacitor, that will change the frequency of oscillation, and that's an important principle which will come into play for our metal detector. So let's build this with parts from our snap circuit kit and see if we can get it to work. Operational amplifiers are available in a variety of configurations. An 8-pin integrated circuit that contains a single op-amp is the popular 741 chip. There are also a number of chips that package 2 op-amps in a single 8-pin integrated circuit. And we even have 14-pin chips that contain 4 operational amplifiers in one package. And this would be the device of choice for a metal detector, but here we're using the dual op-amp in an 8-pin chip because that's what fits best on our snap circuits board. And today I'm using only 1/2 of that chip, just one operational amplifier. You'll find a link to schematic diagrams for all circuits used in this series in the description of this video. The coil and tuning capacitor for this circuit are the ones that come with the snap circuit set. They are designed to resonate together at frequencies for the AM radio broadcast band. So if we can get this to oscillate, we should be able to detect it with an AM radio receiver. First, let's turn on the receiver and make sure it's set to AM, not FM. Then tune to a weak distance station, not a strong one. Then turn on the oscillator and turn the variable capacitor until we hear our oscillator sweeping over the radio station signal. So what causes that tone we hear when our oscillator is tuned close to the frequency of the broadcast station? Yes, it's the beat frequency, the difference between the frequencies of our oscillator and the broadcast station. Understanding that is important for understanding the next step in this project in building a working metal detector. However, before we get to that, we just gotta take a sidetrack and do something fun that has absolutely nothing to do with metal detectors, namely adding our voice to this radio transmitter and broadcasting our voice to a radio receiver. And we'll do that in our next video.
Testing, 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 testing. That comes out. Testing, testing.